Hi, I'm Bradshaw from Hexagon. During this video, we'll take a look at building a full Caesar 2 model ready for analysis. We'll start from scratch and run all the way through to completion, taking a look at various different modelling techniques. We'll also look at various different node and element types. So let's get started. Alright, let's get started and create the piping input model. I'm going to use the same folder and the same units file that was set up and configured in the previous video. So I'm just going to go straight to create a new job file. I'll give the job file a name and hit OK. As mentioned, I'm going to use the same units file as before, and I can tell very quickly, yes, this is the correct units file from the label which I gave previously. So once again, hit OK, and now the piping input module will appear. So I'm going to go through and start entering the properties on the first element, starting with the diameter, which will be 6-inch nominal size pipe. Nominal size input is turned on, so I just enter in 6. For the diameter, and for the wall thickness I want standard schedule pipe, so I just type in S for standard. Okay, material. For the material I'm going to pick from here, I'm going to pick a European material, and I'm going to specify material 1.0425 or P265GH. So I don't know the material number, I'm just going to type in 1.0425 and hit enter. Caesar 2 does the search and presents me with the matching materials. I'm going to pick this top one here, 1.0425 S for seamless, 16 for the 16mm max thickness of this material instance, and 100 is the 100,000 hour creep values, which is typical. I'm not concerned with creep in this particular example, so 100,000 hours is suitable. So hit OK. That fills in the density under the various different elastic modulus values. However, notice the allowable stresses are all 0. That's because this is B313 design code and we've picked a European material. So we need to either pick an appropriate material or an appropriate design code. So I'm going to switch the code to EN13480. Now we have allowable stress values. So for the correct allowable stress values, of course, we need to enter in the conditions. So I'm going to enter in a temperature, one temperature and one pressure in this example, and this will be 220 degrees. And for the pressure in megapascals, I'm going to have 5 megapascals. Okay, now I can start entering the geometry. So no insulation, no refractory lining on this particular example. So I'm going to start by entering in the Z direction 900mm DZ. I'm also going to add an anchor at the start of this element, which is node 10. So double clicking on the restraint checkbox, node 10 is automatically filled in, and I'm going to pick from the drop down list an anchor, meaning restrained in all 6 degrees of freedom. There's also a bend on this element, so I'm going to double click the bend checkbox, and for the bend radius I'm happy with a long radius elbow, so that's fine. On the graphics, the bend is not drawn yet because the direction of the following element is not known yet, so let's create that next element now. To do that, hit the continue button on the left hand side of the classic piping input. That will create a new element. It will automatically increment the node numbers, the default being an increment of 10. And now I'm going to travel in the X direction, and I'm going to go 1.25 meters, so 1250 millimeters, and hit enter. I'm going to add a restraint, but just before I do that, just above the graphics area, I'm going to hit this button here to turn on the display of node numbers. And at node number 30, I'm going to add in a restraint. So I'm going to check the restraint checkbox once again at node number 30, and the type of restraint will be a Y restraint. That is a sit on and a hold down restraint, restraining in the vertical direction. And I'm also going to add in a guide restraining in the translational direction. So also at node 30, so in restraint 2, node 30, and add in a guide. Hit enter and the restraint indicated by the arrows on screen. So let's continue. 30 to 40, this element will be 4 meters in length, again in the X direction. And again at 40 I'm going to add in the same restraints. So a Y restraint, and at node 40 a guide. Okay, I want another 4 meter element, so instead of hitting continue, creating the element manually, I'm going to hit the next button down, which is duplicate element, to automatically copy the element 30 to 40, repeat that at 40 to 50, which includes the repeat of the restraints as well. So continue again. This element will be 3 meters in length, and at node 60 there will be another bend. Continue again. This time I'm going to go in the Z direction, 1.2 meters, so 1200 in DZ, again with a bend. Continue once more, and DY will be going downwards, so that's negative DY, minus 2.5 meters, like so. Okay, so down here is where I'm going to connect to a pump, so I'm going to add in a reducer. So I'm going to hit continue, add in the element which will be 140 millimeters in length. This will be a reducer, as I said, so check the reducer checkbox. And in the reducer data panel, this is where I can specify the second diameter and thickness. So this will be a 6 by 4 inch reducer, and the following thickness will be standard schedule. Alpha is the reducer alpha angle. You can leave that blank and Caesar 2 will calculate an appropriate value. Which leaves me to create the final element for this pipe run. So I hit continue, and this last element, this will be the connection to the pump nozzle, so this will be simply a flange. So I'm going to choose to look up the flange properties from the database. So I'm going to go to this red button over here on the left hand side to access the valve and flange database. And here I'm going to look up a flange. So we've got the ANSI flange database active. There is available a EN-DIN flange database also. For this example, even though I'm using the European standard, I'm going to stick with the ANSI flange database, and I'm going to choose a flange as the type of rigid, and I'm going to choose the class, which will be class 300, which is about right, just about, for the 5-bar pressure rating. And I hit OK, and the flange is created like so. Finishing this off by hitting the restraint checkbox and choosing an anchor located at node 100 at the end of the pipe run. Okay, next going to add the check valve, which will be located down towards the pump connection. So I'm going to locate this just after the reducer. The check valve will be a rigid element, so it's not flexible like pipe. For a rigid element, similar to the flange that we have here, which is also a rigid, if I select the rigid field, you can see for the rigid element all we need is the weight and the length of the component. So I can manually specify the length and manually specify the weight of the check valve, or alternatively I can do similar to what I've just done. I can use the valve and flange database. So the valve will be located on this element which already exists, so I can do this by selecting the element and right clicking on that element and choosing from the right click menu the appropriate option, this time to look up the valve and flange. And this time I will choose a check valve. It will be a flanged check valve, so it will have flanged end types, and once again class 300. But I have some additional radio buttons here. What I don't want to do is turn the whole 2.5 meter element into the check valve. I want to place it at the far end, or the to end, located at node 80. I can also choose to model this either as a single element, which will have the overall combined length and weight of the flange valve flange train, or I can model them as 3 individual elements. For the piping flexibility analysis, that doesn't really make any difference to the results. However, if you wish to perform a flange check, to check for leakage on the flanges, you will need to model the flanges separately. So I'm going to tick the box. There's also a second checkbox for the aforementioned flange checks, which I can activate and turn on by ticking that button here. I'm not going to do that for this particular example though. So just ticking the one flange valve flange checkbox, the to end radio button, and hit OK. So that 2.5 meter element, 70 to 80, is now split into multiple elements, 70 to 72, 72 to 4, 74 to 6, and 76 to 80, the flange, the valve and the flange. Also, to support this valve and also to support the piping and account for any thermal movement, I'm going to add a spring hanger located at the top of the riser. So on 60 to 70, I'm going to select the element and I'm going to check the hangers checkbox and select a spring hanger. I'm going to allow Caesar 2 to size and select the spring hanger for me, so the only thing I need to choose in this example is the spring hanger manufacturer catalogue to select from. As you can see, there are a number available in the list. I'm going to choose Carpenter and Patterson from here, and there's my spring hanger. And now the final thing I'm going to do to complete this model is I'm going to add a second pump connection. I'm going to add a second branch. So the second branch will be a copy of this first one. So I'm going to use the duplicate function to create a copy of that. So I'm going to move into select mode, selecting just above the graphics window select mode, and simply draw a window around the elements that I wish to duplicate. And then I can right click in the graphics and choose the operation to perform on this selection of nodes, which will be duplicate in this case. I'm going to create an identical copy, so you can also mirror about any of the planes as you can see here, but I will choose an identical copy. You can also go into the setup and choose what you want to copy if you don't wish to copy the restraint, for example. And I'm going to choose and specify a node number increment, so this will be a value that's added to each node number in the selection. So I'm going to increment by, let's say, 100. Okay, that's created me a copy of those elements, but there is no common node number between the original pipeline and the new duplicated elements that we've created. So Caesar 2 just places these at the origin at 0, 0, 0. So next I need to specify where I'm going to fit these. To do that I need to create a node, a location to connect to. So what I'm going to do is I'm going to split here and add a new node number in this element here. And I'm going to right click on the element and choose to break the current element, which can be used to add in a new node number. The new node will be node number 55. So Caesar 2 suggests that as a default, just splitting the difference between the to and from node numbers. But the location, I'm going to adjust the location here. I'm going to make this just 1 meter from the node number 50. It's okay. There is node number 55. And all that's left for me to do is connect up these copied elements here. So from 160 to 170, 72, etc., etc. I need to adjust this. So this will connect not to 160, but this will connect to node number 55. So I simply change the node number, the from node number to 55, and hit enter. The components move into the correct position, like so. And the final thing to do is, at this location here where there is a T or an intersection, I need to specify the stress intensification factors at this location, which is done using the SIFs and Ts checkbox. So I will check the box and select the T type, and I will choose type 3, a welding T. And of course we must make sure that the stress intensification factor is applied at the correct node, which is number 55. We could have applied this stress intensification factor at any of the 3 elements framing into node 55, doesn't matter which one, so long as you have the node number set correctly. And that's it, our model is now ready for analysis. I hope you found that useful, but if you do have any further questions, please don't hesitate to reach out to us at Hexagon. Thank you for watching.